Now we explore reflections some more. Section 5.3 is on householder transformations or reflections. On the previous section, we introduced a technique to reflect a vector x about a vector v in the direction u, where we required that x be in the span of u and v, and we had the little geometric illustration of it in section 5.2. In this section, we accomplished this with a specific matrix. I mean, we commented in passing that reflection stuff can be performed by matrix multiplication. First thing we'll do is give the matrix that performs that. It's a fairly elementary computation. So let u and v be orthonormal vectors and let x be in the span of u and v. Say x equals c1u plus c2v. Remember, we define the reflection of x about v in the direction u as x tilde equals negative c1u plus c2v. We simply change the coefficient of the u in that representation of x as a linear combination of the u's and the v's. Consider the matrix H, which is the identity matrix, minus 2 times u transpose. All of this happening, say, in Rn. So H is an n by n matrix. U and V are vectors with n components. They're n vectors. Treating vector U, as written here, as a column vector, we're still operating under the default that all vectors are column vectors unless stated otherwise. So what we've got with this U transpose is the outer product of vector U with itself. Now, let's take this matrix H and apply it to vector X. Matrix H is I minus 2u transpose. Vector X is C1u plus C2u. Apply the identity. We get the C1u plus C2v. C1u plus C2v. So we get that out when we apply the identity, and then we get minus 2u transpose times a linear combination. Bring the scalars out front, as we can do, and that'll give us a u transpose u minus 2 c sub 2 should read u transpose v. Now, when I see a transpose of a vector followed by a vector, then that's an inner product. So we can rewrite this as the linear combination minus 2c1u, inner product of u with u2, c2 to c sub 2 u, inner product of u with v. So the previous can be rewritten in this form. Now, we started all this with u and v being orthonormal vectors. So vectors that are orthogonal, so the inner product of u and v is 0. Vectors of norm 1, so the inner product of u with itself is the norm squared of u, and that must be 1, since we're assuming we have an orthonormal collection of vectors. So we lose this all together, and we lose the inner product. It's 1 is what we get with the second part. And you do the arithmetic. We've got c1u minus 2c1u, leaving us with a negative c1u. And the c2v part has come along for the ride. And there you go, that's x tilde, and that's what we were looking for. So we were trying to produce that vector with matrix multiplication, and there's how you do it. Provided you know that when you're doing the projection, which has to be given in the reflection, which has to be given in terms of reflect x about a vector v in the direction u. So you have to be given those two vectors. And we would need to be dealing with the way we set this up with u and v being unit vectors and orthogonal to each other. The orthogonality we get with this back when we talked about projecting in directions. But we could always normalize vectors, and that wouldn't affect any of the geometry. Okay, so that reflection can be represented by matrix multiplication. We talked in the last section about what a linear transformation is in the usual sense. And then Gentle had some odd sense where he introduced those homogeneous coordinates. Here we've got totally a linear transformation. So reflections of the sense about a vector in a direction of another vector, about vector v in the direction of u. Those are totally linear transformations because they're represented by matrices. All linear transformations in the traditional sense are represented by matrices. Gee, you did that in linear algebra. For orthonormal u and v, this matrix we just defined is a reflection matrix or a householder matrix. That's the title of the section. Some properties of the reflection matrix. H equals I minus 2 u transpose. H of u is negative u being given in the setup. And easily verified. H of v equals v, easily verified. Also, both of these make good geometric sense. If you reflect vector v about vector v, nothing happens. If you reflect vector u about vector v, you get negative of u. Remember, u is perpendicular to v, makes geometric sense. And easily confirm that this is a symmetric matrix, run through there with a transpose. And easily confirmed by calculation that its transpose is its inverse. So it's its own inverse, by the way. A related result is the following. Okay, so what we're doing here, somewhat related to what we had there, in that we're really just changing one component of an input vector. Changing it in a particular way is given here. For non-zero vector x, x1 through x sub n, treat it as a column vector. So I write it as a row vector and then transpose it for spatial reasons. Define vector q to be x1 through x sub n with the modification of the kth component to be x sub k plus the sine of x sub k times a norm of x. In the following conversation, we're using the usual norms, the L2 norms, the Euclidean norm in this conversation. So that's why the subscripts of 2 on all the norms in what follows. Sine of x sub k, let's see, that was 1 if x sub k is positive, negative 1 if x sub k is negative, and 0 if x sub k is 0. Let u be the vector q normalized, q divided by the norm of q. Then if we consider h equals I minus 2 u transpose, this maps x to h of x, which would denote as x tilde, where all the entries of x tilde are 0 except the kth entry, provided x sub k is non-zero. So we're going to, when we apply h to x, we'll get 0, 0, 0, 0, a non-zero entry in the kth entry, 0, 0, 0, 0. So it's looking for geometric interpretation of it. It's really swamped the entries of this vector x and just left us with one of the components. We'll go through the proof. Let's make an observation before we do that. The proof is a little clunky. It's straightforward. It's computational. But we'll see in the proof of this theorem that the kth entry of the x tilde, the image, is actually this quantity here. It's negative sine x sub k times the norm of x. Gentile gives some computations to illustrate this. Page 181 considers this vector x with components 3, 1, 2, 1, 1. So it's from R5. K equals 1. So it's the first component that will be non-zero when we do the transformation. The norm of x is 4, 3 squared plus 1 squared plus 2 squared plus 1 squared plus 1 squared is 16. Square root of gives us 4 for the norm. And when you apply h to that vector, as shown in the book, you'll get out negative 4, 0, 0, 0. Missing a component here, aren't I? Yeah, I should have another 0 there. Should be 4 zeros. Negative 4, 0, 0, 0, 0. As you would expect, the k equals 1, the first component should be, if this is correct, negative sine of x sub 1. X sub 1 is 3, so it should be just negative 1 times the norm of the vector. Norm of the vector is 4. We should get a negative 1 in that first component. So, sorry, typo on the number of components, but we should get exactly this. So that behaves as it should. Now, let's go through a proof of this. Okay, as commented, the proof it's computational, which as I always say means it's should be not so hard to follow, a little uninspired maybe on some of the manipulations, but computational proof. Okay, so we're taking vector Q as given here. Let's find out the norm of vector Q squared. Well, we just square up all the components. Okay, nice smooth sailing until we hit the kth component and we get that thing squared, and then smooth sailing until the end. So square all the components. This is what you get for the norm squared of Q under the Euclidean norm, the L2 norm. And we've got an x1 squared plus x2 squared up through x sub k minus 1 squared. There's an x sub k squared, an x sub k plus 1 squared through x sub n squared. Collect all those subscripted x's, which are squared, together, and that gives you the norm of vector x squared. Those were the components of vector x. All right, but you're still left with this little bit here we got from squaring the kth component of Q. We're left with a 2x sub k sine of x sub k, norm of x. Well, the sine of x sub k is plus or minus 1. When I multiply it by x sub k, we get the absolute value of x sub k. If x sub k was positive, then we just get 1 out, and x sub k equals its absolute value. If x sub k was negative, the sine of x sub k is negative, and we get the negative times negative. We ultimately get the absolute value in that case. And this holds as well if x sub k is 0. We're interested in x sub k non-zero though. So we'll combine those two to produce an absolute value. Over here we've got a sine of x sub k squared. Well, it's a 1 or negative 1. And when you square it, it's 1. So I can just drop that. And remember, we're considering x sub k non-zero, so don't worry about it equaling 0. So we pick up x sub 2 norm squared from this, a 2 absolute value of x sub k times norm x from that. We had combined all these squared x sub k's to get a norm of x squared. So we've got 2 norms of x squares, and we got 2 of these things. This involves a norm of x as well. Let's pull that norm of x out, and we get 2 norm x times a quantity, norm x plus absolute value of x sub k. All right, so there's the norm of vector Q squared. We'll appeal back to that around the end of this computation. Let's find the ij entry of the outer product of Q and Q transpose. Okay, Q is treated as a column vector. Our vectors are column vectors unless transposed, in which case they're row vectors. So here we've got a column vector times a row vector. So when we do our row times column multiplication, the ij entry will be the ith component of this column vector times the jth component of this row vector. It'll be q sub I and q sub j, where those indicate the components of vector Q. Simply from the definition of how you multiply matrices. Now, the components of Q, they're the same as the components for X, except in the kth component. So if we stay away from K, Q sub ij is going to be X sub I, X sub j. If we hit K, then we're going to have to use this thing here. So if I equals K and J doesn't equal K, then the ith component, Q sub I, is this. Jth component is X, is the same as X's jth component because J doesn't equal K. Interchange that. Suppose J equals K and I doesn't. Okay, we get the X sub I here, and the Q sub J, Q sub K is this involved quantity here. If I and J are both K, then we get 2 copies of this thing here. So Q sub K would be this product, that quantity squared. We're going to introduce y, let y be x sub k plus the sine of x times the norm of x. Change of variables, it's going to simplify some things. This y sub k, this quantity here, the thing I keep referring to, this quantity here, pops up a lot. So let's simplify that a little bit. Then this becomes y sub k times x sub j. This becomes x sub I times y sub k, and this becomes y sub k squared. Because we're about to put all this stuff in a matrix. All right, so QQ transpose is a matrix, an n by n matrix, and it looks like this. Yeah, we've just got corresponding parts of the x's multiplied together as we would in an outer product. x1 times x1, x1 times x2, x1 times x sub k minus 1, x1 times x sub n. Yeah, it's the kth column and the kth row that's going to be weird. And we've got a formula for these from the previous slide. All right, so instead of getting x1 times x sub k, oh yeah, we'll have to use the y sub k because of the entries in the Q vector. So we get these y sub k's all along this kth column is the second part of that product. And we get y sub k's as the first part of the product along the kth row. And there's your y sub k that we were talking about before. So outer product expressed in terms of components of this and this. Hey, the components of this and that, the Q transpose, the components are the same as they are for X, except in the kth column and in the kth row. So that produces this for Q transpose. All right, next slide, we're going to multiply this by vector X. We're going somewhere with this. We're going to multiply this by vector X. So think of a column vector strewn along over here on the right, x1, x2 through x sub n, all subscripted x's, vector X. When you do the product, Q transpose times vector X, you'll take this first row and multiply it by that column. That'll produce x1 times x1 times x1, x1 times x2 times x1, x1 times x sub k minus 1 times x1, x1 y sub k times x1. So let's see, did I read? I went through that wrong. Let's see, we're going down this column. I multiplied this first one by an x1, the second one by an x2, this one by an x sub k minus 1, this one by an x sub k. I think I went through that wrong previously, up through x sub n. I'm trying to foreshadow what's on the next slide. So we'll have an x1 times x1 squared. We'll have an x1 times x2 squared, x1 times x sub k minus 1 squared. Let's skip that one. x1 times x sub k plus 1 squared up through x sub 1, x sub n squared. So we get x1 times the squares of all the other x's. Here we'll get x2 times the squares of all the other x's. Here we'll get x sub n times the squares of all the other x's. And we'll have to deal with what we have to deal with when we hit the kth column and the kth row. All right. So if you'll take Q transpose times X, like I said, you get x1 times the sum of all of the other x's squared, except in the kth component. You get x2 times the sum of the squares of all the other x's, except for in the kth component, and so forth. Got a little explaining to do down here in the kth entry, but other than that, the pattern's the same. Now, about that, except for the kth component, here we've included, we've sum from L equals 1 to n, including k. So there's somewhere in here, there's an x1 times x sub k squared. But I don't want that, so let's take it away. Let's take away the x1 times x sub k squared, subtract that off, and replace it with x sub 1 y sub k, x sub k. That y sub k right there is replacing an x sub k because of what we had in terms of the matrix. Let's go back real quick. Right there. The pattern is x1 times x1, x1 times x2, x1 times x sub k minus 1, x1 times x sub k. No, I mean x1 times y sub k. The x sub k, in a sense, it's replaced with a y sub k. So remove what you would get from the sum of having an x1 times x sub k squared, remove it with a negative, and replace it, add in x1 y sub k, x sub k. You've replaced one of the x sub k's with a y sub k. And that's exactly what you need in terms of taking this matrix product. Do that throughout. So the pattern is not complicated. You subtract x1 times x sub k squared, x2 times x sub k squared, and so forth. And then add in x sub whatever, y sub k, x sub k. In the kth row, we had not x sub k times the sum of the squares, but we had the y sub k in that one. So we'll take y sub k times the sum of all those x squares, just like we did upstairs. But this includes an x sub k squared. I need to replace one of those x sub k's with a y sub k. So subtract off the y sub k, x sub k squared that would appear when L equals k. Subtract that away and replace it with this. It's the same pattern. Slightly more complicated. I would expect to see an x sub k first, but we don't. We see a y sub k first. Then I'd expect to see a y sub k, and we do, and then an x sub k, and we do. These all end y sub k, x sub k. They are all of those y sub k, x sub k's are preceded by an x1, x2 through x sub n, except for in the kth spot where it's preceded by a y sub k. So you should believe that that's what you get when you multiply q transpose times vector x. Hey, these sum of components squared, that's just the L2 norm of x. So let's replace those summations with L2 norms as we've done throughout. Pattern is the same throughout, even in the kth row. I'm just making a substitution. Over here, let's see, we've got an x1 xk in both of these. We've got an x2 xk in both of these. Let's factor the x1 x sub k out. That'd leave us with an x sub k, I'm going to minus up front, minus y sub k, x sub k minus y sub k. And that pattern holds throughout the right-hand part of the computation. Hey, x sub k minus y sub k, we introduced the y sub k earlier in such a way that we can solve that y sub k formula introduced earlier for x sub k minus y sub k and replace this, and that's what's next. So carrying on the computation, we're still working on q transpose times x. Somewhere in here, I expect to see an identity minus, what was it, 2u transpose. So we got a little ways to go before then. But here's the computation so far. We got the minus out front. Yeah, I got a difference here. All right. We had y sub k equals x sub k plus the sine of x sub k times the norm of x. That's what we define the y sub k to be, to briefly simplify our computations. So x sub k times the x sub k minus y sub k, so much of that stuff we had along the right-hand part of the computations can be replaced with x sub k times x sub k minus y sub k would be the negative of this. Negative sine x sub k times the norm of x. Oh, there's that sine of x sub k times x sub k thing again. That's absolute value again, with a negative sign out front. So we get negative absolute value of x sub k times the norm of x. All right, so we're replacing x sub k times x sub k minus y sub k with this. Let's go back to the previous slide. X sub k minus y sub k. That's always in the right-hand part here. It's preceded by an x1, an x2, an x sub k minus 1. Whoops, a y sub k, and x sub k through x sub n. So we're replacing this last little bit of stuff by that quantity we just saw, producing this. So we replace the x sub k times x sub k minus y sub k with this. And sure enough, we've got an absolute value of x sub k times a norm of x throughout the right-hand part. Also, there's a negative, and we had a negative in front of the right-hand part on the previous slide. So we could change that to a positive. So q transpose x is this thing here. All right, I told you it's computational. Can't argue with the computations. In that sense, it's straightforward. We had the norm of q squared given by this quantity here. I called attention to it as soon as we defined vector q. First thing we did was find its norm squared, and it was exactly this. So if we look at I minus 2u transpose x, then we get the following. All right, here's where we're going. We're supposed to get out a vector that has zeros in all its components except for the kth component. So that's what this computation is supposed to show. Vector u was defined as q normalized, first slide, I think. So when we take I minus 2 UU transpose, we're really taking I minus 2 Q over its norm times Q transpose over its norm. Collect the norms together in the denominator. So we get I minus 2 Q transpose over the norm of Q squared, the L2 norm. Let's simplify that by introducing a norm of Q squared as a coefficient to the identity matrix. Then I can certainly take this norm squared of Q and distribute it back, division, and we get the same thing. We get cancellation there. Q is a non-zero matrix, non-zero vector. We're multiplying that by vector x. There's the vector x. This norm of Q squared is going to be in the way briefly. So we'll pull it out as a coefficient and see what we get with those computations. All right. Norm of Q squared times the identity matrix. Why, there's the norm of Q squared right there. So multiplied by the identity matrix, it produces this thing. Then that's going to be multiplied by vector x. So we'll pick up components of vector x, x1 through x sub n, including x sub k. We're multiplying it by vector x this time. So norm of Q squared, identity times x is exactly this part. Now we're subtracting 2 Q transpose. We had the Q transpose stuff as given above. Subtract 2 Q transpose, and that'll produce exactly this. So let's go back and look at Q transpose times x again. Q transpose times x was exactly this. We're going to multiply this by -2. That's what it amounts to. Kth one was interesting. Back to where we were. Kth one's interesting. Got a y sub k. All those -2s. There's a -2. It's been distributed. So we just copied that part from the previous over. And I minus 2 UU transpose x. Supposed to get a bunch of zeros out. And you do. This first component is 0. Look what you've got. 2 norm of x times norm of x times x1. So that's 2 norm of x squared times x1. 2 norm of x squared times x sub 1. So distribute, the first part cancels with this. Distribute, second part gives 2 norm of x times absolute value of x sub k times x sub 1. Over here we've got minus 2 norm of x, absolute value of x sub k times x sub 1. And same thing throughout except in the kth row. So we get cancellation, that first component 0, second component 0, k minus 1 component is 0, k plus 1 component is 0, and so forth. So we get a whole bunch of cancellation except in the kth component. So this equals ... this. 0, 0, 0. Here's a kth component. I just copied what we had before. We'll simplify it now. Followed by a bunch of zeros. And the whole thing's divided by the norm of Q squared. So let's manipulate this long kth component and see if we can't simplify that down. It simplifies down quite a bit, in fact. Okay, what's common here? We've got a 2 here in this term. We've got a, well, let's factor a -2 out of this second term. Factor a -2 out here. Rearrange things a little bit. We've got a, let's factor a -2 norm of x times y sub k out of these two terms. -2 norm of x, y sub k. That'll leave a norm of x from the first one. -2 norm of x, y sub k will leave an absolute value of x sub k in the second one. Factor a -2 out, produces this. Next, these in turn have some stuff in common. They've got 2 norm of x times this summation. 2 norm of x, this summation. This one also has a factor of x sub k. This one also has a factor of minus y sub k. So factor that 2 norm of x times norm of x plus absolute value of x sub k. Factor that out, you're left with an x sub k minus y sub k. And we had upstairs that x sub k minus y sub k was negative sine x sub k times the norm of x. That we've used recently. So we can replace the x sub k minus y sub k with that quantity there. Remember, you still need to divide by the norm of q squared. Remember, the norm of q squared was this thing here. So let's substitute that in. This cancels. Got the same thing here. We're left with this negative sine x sub k norm of x, and that's all in the kth component. So we get the vector 0, 0, 0, 0, 0, negative sine x sub k norm of x, 0, 0, 0, 0. Claim was this mapping would produce a vector of all zeros except in the kth component. We get 0 in the kth component as well if x sub k was 0. But if x sub k is non-zero, then we get this in the kth component. And that's what the theorem claimed. So the theorem claimed all entries of x tilde, which we just found, were zeros except for the kth entry. We already observed that's what you get in the kth entry. So there's the proof of that. That takes care of section 5.3, reflections. We're going to look at rotations some more next time in section 5.4. I will see you there. Have a nice day.